right. Thank you all for joining this rendition of the NSBP KITP Innovate seminar. Um, we are happy to introduce Dr. Maurice Roots. So I will read off his bio and then head into his talk. So Dr. Maurice Roots is a NASA postdoctoral fellow, continuing his work in atmospheric physics with a focus on air quality and boundary layer dynamics. He earned his PhD in atmospheric physics from the University of Maryland, Baltimore County, or UMBC, where he also conducted pioneering research on the influence and characterization of nocturnal low-level jets on air quality in the mid-Atlantic U.S. He earned his Bachelor of Science in Physics from Hampton University with minors in nanoscience and mathematics. Dr. Roots is a recipient of the NASA Finest Award, a GEM Fellow, and an alumnus of multiple NOAA EPP programs, including NCASM, CESS, RST, and the Hollings Scholarship. His expertise spans active and passive remote sensing techniques, as well as multi-platform observational campaigns. He has participated in several NASA-led field experiments aimed at advancing air quality monitoring and predictive capabilities. Passionate about science, the outdoors, and mentorship, Dr. Roots is committed to pushing the boundaries of atmospheric research and inspiring the next generation of environmental scientists. And his talk today will be profiling pollution, multi-instrument observations for 4D air quality science. So, Maurice, we have your attention now, and we will be intently listening to you.
Okay. Thank you, Alan. I appreciate that. Um, so this talk is really focused about uh, the work that I've done and some of the stuff that I plan to continue doing, and specifically in profiling of pollution. And I'll talk a little bit more about what that sort of specifically means. But you can kind of get a sense of that from what's on the left side, which is a picture of a lidar on the bottom in just an urban environment, a balloon floating through the air, and then a satellite looking down. And what I'm going to try and highlight is the importance of having these multiple perspectives, these multiple instrument observations to really understand things on how things are changing in space and time, for something as complicated as air quality or pollution transport. Um, so the uh, the landscape for air quality science is currently evolving, as we've done a lot of work on reducing emissions. If you follow that magenta line on the left-hand side, you can see that the percent change since 1970, which is on the far left, is when the Clean Air Act was created. It's when the EPA was founded, and we've done a lot of work in reducing our anthropogenic emissions. At the same time, we've done a lot of growth as a country. But still, for some of the major uh, pieces of what we consider pollution, or what's in these six criteria pollutants, ozone and particulate matter, a lot of people are still being affected by these um, constituents. PM, I might refer to as aerosols, and ozone. So it's about 130 million people in the US that are still being affected by levels that are higher than what the EPA says is allowable for ambient outdoor um, concentrations. And if we take another view of that, sort of this transition since the 90s, which is one of the major updates to the Clean Air Act, took place, we see that ozone, I've highlighted that green line, we've kind of stagnated in the change that's happening there, and that's a result, or that results in why there's still so many people that are being affected by high ozone levels at the surface. And it turns out that it's actually a really complicated process that's much more than just on the side of regulating emissions. As you saw by some of those figures there, one of them was kind of taken from um, when wildfire smoke was coming through several of the cities on the East Coast and kind of just took over the skies. And we saw a lot of increases in those same pollutants I was just mentioning, ozone and particulate matter. And it's a complicated balance, sort of dance almost between um, the anthropogenic emissions, the pollution that's coming from our activity, and then the terrain itself, being that most of our cities, our most populated cities, are on the water or in the mountains or in places that have really interesting surface characteristics. And then along with that comes, not just people living and driving cars and all of that kind of thing. There's also a lot of industry, like for ports. Most of our cities are on the water because they're port cities. And so you have this dance, as I mentioned, between what's happening in the natural space of just things being formed by normal diurnal chemistry in the atmosphere, and then the influence of the emissions that are coming from our activities, and then the differential heating, as it's labeled on here, between the different surfaces, and then orographic effects from the in like mountainous terrain, and all of these kind of things go into the importance of understanding in multiple different ways what's happening here. And to do that, some of the things that are listed on here, same as I showed in that first title slide, is profiles from the ground using things like lidars, launching balloons that give you an in-situ perspective, and then the satellites that cover a large spatial area and gives you that top-down kind of view of what's going on. And putting those all together is kind of what we know now is like the only way to really effectively tell the story of when, where, and how these pollution events are happening. So what I'm going to continue to talk about is in my work is what I've been focusing on is this synoptic and transport influence, that piece of the puzzle, because that's one of the um, uh, much harder to mitigate and regulate pieces that is still left unanswered in terms of its quantitative effects to the surface air. So with all of that kind of understanding, it's like, well, what do we do about that? What's the direction? Where are we going to go? Those questions have kind of been pieced together already. And there's a thing called the decadal survey. NASA does a survey from all the scientists and working groups every 10 years. And there's another one coming up soon, actually. But from the most recent one in 2017, we have these few questions that are particularly pertaining to my work in W1, 5, and 7 is weather and air quality. And the science that we're looking for is like, what are the processes within the boundary layer? And I'll explain what we mean by that more specifically in a minute. In exchanging air with the surface, mass and momentum, that being the constituents that are in the air as well, and how is that impacting our air quality models? How is that impacting the way we predict these kind of events happening in the future? And then what are the processes that are um, uh, determining why we're seeing things in certain places at certain times, and what are the concomitant or natural impacts that are happening that are degrading human health, agriculture, and ecosystems? Because the pollution, if it's bad for us to breathe, it's bad for the animals, it's bad for the land animals and marine animals, and as well as the plant life too, because they're also taking these things in when they respirate. Um, and then lastly, specifically about ozone itself, which is what my main focus is. Um, and what are the trends that are happening on the natural scale, and that are affecting the composition and chemistry on scales that are on the short term and also relevant for climate. So um, ozone, I've mentioned that several times, but you, not everyone might be familiar with what ozone is or its importance or that kind of thing. I'm sure everyone's heard about the ozone layer. And actually, let me turn on my little laser pointer. Can you guys see that? I think so.
Yes.
Okay, cool. So the ozone layer that's in the stratosphere, way up high, and that's where pretty much about 90% of the ozone on the planet resides. And then there's just a little bit left that's in what we call our surface air, which is close to this boundary, which is coupled to the surface itself. And that's what we're talking about here. So ozone itself is a powerful oxidant, because it's three oxygen molecules in this instance, right? And um, it's just showing you how ozone can degrade um, plants, and then that leading to agriculture and a lot of losses in terms of economic value and then food production. And this one in the middle is kind of taking it all the way back to why even um, air quality in the EPA was formed in the first place, where this is a picture from LA, and a pretty famous picture, but it kind of highlights how just in the day-to-day life is affected by um, the just large amount of mass that's dumped into an area from large amounts of anthropogenic activity, and the emissions that are precursors to ozone that form into ozone create things like smog, and that can really degrade just quality of life as well as the habitability of an area. LA is also one of the regions where it's complex air quality situation, large port, a lot of people living there. That whole kind of uh, conceptual model I just highlighted a second ago. Um, so when I hope that kind of orients into ozone and sort of the importance. If you have any questions throughout the rest of the talk, really, like you can ask pretty much at any point. Raise your hand, or I'm sure somebody's moderating, but feel free to do so. Um, and this bottom plot here is a tile plot. You might see another one of these coming up, but the way to read this is that yellow is high but not past regulatory levels, and then orange is right past regulatory levels. You never want to see a purple, and sometimes there are reds, but if you can see that trend there, it's gotten a lot better in like the last 10 years. There's still some events here and there that are happening, but for the most part, we're doing pretty good, but still with um, these tightening on regulations, um, why are we still seeing some of these events happen? And it's because of this whole complex uh, dance that I've tried to highlight for you here. So what do we do about this in terms of understanding, and what's the science that we need to be going for? I talked about the questions, but sort of how do we do this? And we do this by the multi-instrument perspective. And what those instruments, and what they do for us, is that we need the lidars, as I mentioned, and the sounding profiles that are on the balloon-borne um, payloads to get uh, what's the height of the atmospheric boundary layer, what's the temporal evolution of that decoupling zone from the surface. We need profiles of winds so that we can understand the transport mechanisms. And then we need profiles of the gases and the particles to understand the composition. That's the profiling of pollution that I've mentioned. And to do that, we need things like ozone lidars and NO2 lidars, which we're still working on. Things like passive instruments like Pandoras and aeronets, and as well as ozone sondes, which are payloads that go on the balloons, but they measure ozone along with the meteorological variables at the same time. So this uh, slide I have is kind of like an infographic that we take for outreach events, and it kind of shows all these QR codes should work, by the way, too, so you can scan those. This kind of takes you through the path of how we specifically as NASA in relation with the EPA and with NOAA are able to do science in the space of air quality, and then also communicate that to the people that live in these areas that are affected. Um, so this is kind of a nice little way to put all of that together and visualize like the whole piece of really doing all of this kind of work. And then this is sort of on the day to day as it is like current. But what we do in a intensive operation, as Alan mentioned in campaign science, is this is a big part of what we do in terms of understanding specific key processes for specific areas. So this is a campaign that we did a couple years ago in Houston, where we're trying to understand the local mesoscale transport mechanisms as involving with the city of Houston and all of its refinery operations um, and gas production in the whole, Houston, greater Houston area, where you have this Galveston Bay, large body of water, and then you also have this the Gulf that's right there as well. And we're trying to understand with all of these different measurements put together that are measuring different things in different locations at different times and resolutions to try and create a data set that gives you the availability of tracking and answering these questions about spatial temporal variability. And these two slides, these next two, are about kind of just like a highlight of what happens when we do these kind of campaigns. This is not anywhere near the first one, but this is one that I have um, sort of more that I can show at the moment for the work that we do in this kind of situation. So if you look on the left, it's kind of where the campaign idea kind of starts, is that we look at the trends and we say, okay, well, there's this thing that keeps happening year after year in this specific sort of time domain or region, and we're going to try and figure out why that's happening. And then we get uh, everyone comes together for an intensive, and in this case, this was during August and September in Houston, and we coordinate and we launch the balloons and we run our lidars, and we there's aircrafts that are doing the same thing and taking in-situ samples and coordinating all of this kind of stuff together to even over the water too, to get measurements at strategic locations for the benefit of mapping out as close as we can to this 4D perspective of what's happening. On the top right, that's on the top is the ozone lidar from the lidar instrument that I work on at NASA Goddard, called the tropospheric ozone lidar. That's NASA GSFC Tropos. And then right below it is our ceilometer, which is it's a sort of like a proxy for the aerosols or particulate matter that's in the air. And from that, we can get the boundary layer height. And that's kind of what I'm highlighting here, is that this is us putting all of that information together with the sondes being these vertical streaks here, the surface at our site. At the bottom, boundary layer height coming from aerosol gradient, from the transition in that mixing, and then looking at the aerosol loading in that situation. And with all that information, what we do with it is we can kind of do uh, backward trajectory simulations to get us a best guess at where the air had come from, and from the lidars, and where we're getting a vertical profile resolutions like 10 meters on average, um, sometimes all the way up to like 10 kilometers. We can kind of see things that are like mixing down from lofted reservoirs, or transport events that are happening really shallow, or just random things like this little blip below 500 meters. And you can't really get that if you're only looking at the surface. You don't have all of this information, all this story really that kind of puts together where the air came from, and then also where it's going. So it's really important to like kind of have all of this stuff together. And so this one is kind of a little plug, but this is kind of one of our best campaigns to date. This is actually a super campaign that happened last year, or 2023. Um, we called it Ages Plus. The plus is because it's a campaign of campaigns. Each of those letters is its own campaign, and it was um, because of COVID, things that got pushed, and so we rescoped everything, and everybody kind of coordinated together to do one giant campaign across the United States and in really key strategic areas. And if you'll notice, each one of these panels is a place where there's a large body of water and a major city, as I was trying to highlight earlier, the importance of that kind of thing. So, we got something in the chat. Oh. So this one here in the middle is where I'll be focusing soon. That work is still ongoing, so I'm not going to show it, but I hope you get the idea of where it's going from the rest of the talk. In that this situation here is we have four of the lidars, four of our ozone lidars with winds somewhat co-located, as well as aerosol profiles and the sondes, and pretty much all of that mixed together so that we can get as close as possible to understanding things happening in that sort of four-dimensional framework. So on to, I'll just briefly go through this. This is kind of my work that I've been doing, and how it feeds into the decadal survey. So I've been studying the impacts and characterization and the influence of a phenomenon called the mid-Atlantic low-level jet. And so I'm just going to walk through this first paper on the left, and then I'll maybe summarize at the end about these two and what I'm working on right now. So this is the sort of another orientation slide, because I've said boundary layer several times, but this is sort of the conceptual schematic of what the planetary boundary layer is. And so this is during the day, you have the surface being heated, and now it's rising in elevation because of convection. And at some point, the convection, the rise, the heating associated is too far away from the surface to be still coupled. And so that gradient there becomes the planetary boundary layer. And then when that transitions into the nocturnal period, you see a decoupling of what's in the sort of atmospheric boundary layer, this the highest extent of mixing. You get these zones that situate where you have a stable nocturnal boundary layer that's more associated to the surface layer, and then you have a residual layer that sets up, and that's kind of where a lot of your pollutants kind of reside during the nighttime. And so, as I sort of hinted at, in the daytime, you're getting ozone being produced by another complicated dance between nitrogen oxides and volatile organic compounds, as the VOCs. When they react with light and heat on the volatile organic compound side, you get a production of ozone. During the nighttime, that process sort of reverses, and the nitric oxide that's been produced reacts back with the ozone and then converts back into diatomic oxygen. And so you get this uh, curve where you're on your surface, you have ozone increasing during the day, decreasing at night. You have NO2 decreasing as the ozone is increasing, and then NO2 increasing at night as the ozone is decreasing. But sometimes that doesn't happen in that sort of way, and that's because of the dynamics. And so during the day, you have the friction from the convection creating eddies and turbulence. And when that goes away, your velocity vector for your particular area starts to shift, and it goes in this rotation pattern that produces a phenomenon called a low-level jet. And so that's what I've been studying in the mid-Atlantic area and a little bit in a few other regions. And this phenomenon is sometimes responsible for pollution transport and injection into the nocturnal boundary layer as it rides on top of the nocturnal boundary layer and gathering those pollutants that are still left in there and pushing them further down. So to orient you on the geographic situation, so for the Mid-Atlantic region, this is a snapshot here, and we have the Appalachian Mountains and increasing elevation towards the west, and then we have this Piedmont Plateau sort of region in the green, and then a very flat uh, coastal environment in the yellow that's has a steep drop as well. That's what that fall line is. And the low-level jet has kind of been reported to set up in that in between those sort of extremes in this like sort of flat area and be a mechanism for transport overnight on mesoscale distances. And the first paper that I mentioned is about an ozone exceedance that happened in Maryland that was correlated to low-level jet and transport of smoke from Canadian wildfires into the region. And this is taking place right here in this May 19th of 2021 event. It's pretty early before the typical ozone season, and it also is responsible for some exceedances that happen in places that are not very typical. The black circles here are where the ozone exceedances were noted, and as you see, it's not really in the what you would expect being associated to the cities or to like breezes from the Chesapeake Bay. In these counties here, we're seeing ozone exceedances where they haven't had hardly any. I mean, maybe, well, I think one of them had one in the last 3 whole years. And then they're leading the exceedance, where Frederick County was reported to exceed up to 78 parts per billion. And the max requirement is at 70 parts per billion. And so an 8-hour average is what we're looking at. So over that time, that's quite a lot for a rural site, and it's sort of unprecedented. But in this situation, I remind you that they're sort of right in line track with this low-level jet path. And so um, that alone kind of prompted us to study, okay, why did this happen? What's going on here? And we have to use what we have available to us, being this multi-instrument super site, as I labeled it on here, where that star is. And at that particular location, along with the surface network from the Maryland Department of Environment, uh, we have sondes that are being launched that's getting us that really high resolution ozone profile, but it follows the wind. Then we have a radar wind profiler, which is a 915 megahertz um, wind profiler that can tell us, wind speed and direction as well as vertical velocity. And ozone lidar, that's what I primarily work with at NASA Goddard, and that's getting us high resolution ozone profiles, as well as salometer, as I mentioned, which gives us the aerosol portion. And I've also used in the analysis Aeronet and Pidor, which are the passive systems, which are really good for getting you things like column amounts, and they have a much more extensive network. I won't be showing those for like the essence of time, but I do have, in my articles is um, been discussed before. So to go over the surface network, um, this is a really important figure here, but you can see that in the nighttime, that's when that shaded region, we're getting increases in ozone. So those increases, as I mentioned before, are not supposed to be happening. And so we're trying to figure out why were those happening? Why are we seeing in a rural site like South Carroll, that's the blue line, why are we seeing ozone uh, up to 51 parts per billion, which is sort of like a number you would expect during the daytime, um, in the middle of the night? And so then we see later in the day, during the sort of the convective part of the day, this sort of 90 ppb block of ozone moving from A to E, that's from east to west across the whole state. And so that's like extremely interesting. And when we look at the LiDAR observations, we can see LiDAR plus surface plus the ozone sun. We can see that there's a polluted reservoir of ozone that's there. And so we think that there's a dynamic effect, and that's partly with the mixing from the residual layer, as well as this wall of ozone that's being pushed across the state of Maryland. Um, so in that, you can sort of see it in here, but there's some pretty interesting gradients that are associated with the low-level jet, which I'll highlight on the next slide, that are showing us that there is an intrusion of that polluted residual air into some of the surface air. And that's the result of that uh, increases in the nocturnal space. And so that's this figure here. On the top, that's the wind speed, the horizontal wind speed. In the middle, that's the direction. Note the uniform direction coming from the southwest. That's the typical direction of the mid-Atlantic low-level jet as it's going parallel to the sloping terrain, as well as really strong vertical velocities pushing air downwards during the low-level jet. And then the same thing that we see even stronger during that time of the wall of ozone moving in, that's coming from this transported smoke from Canada. And so this is kind of the top-down perspective for that. Looking at, we see air mass transported from a string of fires over above Minnesota, moving into our air and then sort of being scraped off by the turbulent downbursts of the low-level jet and pushing that into the surface air. And then all of that being exited from our area as it moves further towards the west. And so on the right here, or on the left, this is back trajectories and a forward trajectory coming from a trajectory model run by NOAA called HiSplit. And on the right, this is the MODIS satellite instrument getting us aerosol optical depth. So this is a way of understanding sort of how much aerosols there are in the air, how much particles there are. And we can see that if you follow the red gradient here, you see this very similar shape as the trajectories. And so this is kind of that's that whole figure put together. It's my favorite one in the paper, and it just kind of sums up the way that you have to have all these things together to get that full story perspective. Um, and it's really important to have as many of these sites as we can, and that's why we do our campaigns. Um, and we can learn really interesting phenomena that can happen where you have a confluence between transport smoke and which is synoptic orientation, and then you have the mesoscale dynamics that are sort of sometimes strictly like diurnal with a certain situation in terms of location. And bringing those two things together, you can get exceedances that are unprecedented, especially in rural areas where you don't even expect such a thing to occur. And so this is kind of the end of my talk, and I'll just leave it with some um, sort of like summary slides and some of the other pieces that go to this. This one is about, I was interested in, well, can we, like, what more can be done about looking at the low-level jets in this specific area? So I have done a characterization. This is that middle panel that I showed, and sort of that first slide about my work specifically. This is sort of the typical low-level jet you can expect from the mid-Atlantic region if you're looking at vertical wind profiles over time. Um, and then this is what I'm working on right now, which is kind of taking that same idea and then broadening that to the data sets that we have available and that we've recently come to have as a sort of long-term record of these kind of profiles along with the surface networks. And we've kind of grown in this space to be able to look at this on a much longer time scale, as well as much more detailed, especially with the coming analysis of that our most recent campaign, where we had 4 lidars strategically placed around the Long Island Sound, and we'll be able to get a similar analysis for several months, uh, and that's where I'm going with that. Really excited. And then leading into, okay, now we have that, we've got the characterization, we've got um, the detection phenomena and all of that. Now, putting all of that data together, and then let's understand, quantify, okay, this particular event, how much is it contributing to um, our ozone budget? Is, what's that concomitant piece? What's the quantification on that, the natural occurrence of this getting into our surface air? And I'll stop there.
All right, thanks so much, Maurice, for that talk. We do have a question in the Q&A, and I saw somebody's hand raised previously. So yeah, please put your question in the Q&A box, and I'll get to all of them. So from Nkiru Campbell Ubarike, we have a question. Has the stable nocturnal boundary layer been linked to worsened respiratory symptoms in people at night?
To answer your question directly, has it been linked? Um, n- Not necessarily to my knowledge, hasn't been linked to worsened respiratory systems in people at night. When most people are asleep at night and indoors, but the what happens in the nocturnal um, is is directly affecting what happens in the um, uh, early part of the morning. So what I didn't say here is that what you can also see is the slope here. This is a very steep gradient for um, ozone production in the morning. I did the calculation. I don't have it on this slide, but it's much higher than it should be. And so that lets us know there was a lot of precursors that were um, flooded into the surface air, and those precursors being that, as I mentioned before, it's like when you have, your nitrogen oxides and volatile organic compounds, um, both of those in different ratios create ozone, and that's a predominantly photochemical process. So when the sun comes up, you getting near UV light hitting onto uh, an NO2 molecule, you're going to get an increase in ozone because it's going to photolysize. And so, specifically during the night, um, I'm not aware of something direct like that, but definitely in the early morning.
All right, thanks for that. Yeah, people in the audience, please do put your questions in the chat. We have one from Richard Braxton. Do aerosols affect PBL or surface heating due to sunlight absorption or scattering?
Oh, absolutely. Yeah, that's um that's um, a pretty well-known process. We're still trying to learn a few things about it specifically, in terms of the PBL height. So, sort of getting at a direct relationship of what the influence of the PBL height is, in relation to aerosol loading, like above. Um, but yes, if you have, you know, attenuators in direct line with your source, you're getting less energy to the surface. Less energy to the surface means less convection. Then there is a sort of a tricky part that comes in with that is things like the greenhouse effect, because you can have long wave radiation bouncing um, between these, between your like attenuators, whatever they are, could be clouds as well. Clouds also have aerosols in them, and um, that can complicate the system a little bit. But absolutely, aerosols affect the boundary layer and the surface heating, because they're a lot of times blocking, um, not that much, but sometimes with like really like dense smoke when it comes overhead, um, you can see that effect much more clearly. And same thing, like with a cloud, when cloud goes over your head, it feels nice because the sunlight's not on you. A lot of energy has been kind of just dissipated straight from there, and then that doesn't get to the surface, and then so you decrease in those eddies. Those kind of measurements are like really difficult, but um, it's definitely in the next phase of things to be more detailed on answering that.
All right, thanks for that. Um, while we wait for maybe another couple of questions, I had one question. So I know that at Brookhaven over near Long Island, there's some researchers that do research with planes to monitor wildfires. And then we had a previous speaker in the Innovate seminar who mentioned use of drones for calibrating instruments to detect for effects in dark energy. So that's more astrophysics. But is there any use of small devices that can fly, like a drone or something of that sort, in your instrumentation that you would add besides the balloons, or are the balloons doing enough work in terms of like getting your instruments up there and working with everything? Is there any advantage, maybe?
Yeah, I'm looking if I have a slide to go along with that, but so you're another great question, but also complicated. So for the hmm, I'll just stay here. Um, so actually, this group here, the rocket group, this is from the University of Alabama, Huntsville. They uh, had this one labeled C-ray. That's a something on the lines of like a Cessna. Um, and they were stationed here in in Kenosha, near Milwaukee, in between Milwaukee and Chicago. Um, took their mobile system out there, flew their plane, and there was, I believe, it was also a drone that they had with them. Um, the drone is, again, because you have to play on the strengths of everything. The drone is not really a system that's going to replace a balloon or going to replace the lidar, but they have their strengths in other areas. So one of the issues with the drone is that you can't fly to 10,000 meters. The FAA only lets you go but so high. Um, but then there's also like uh, there's your how big and rugged your drone has to be scales with the weather that you're gonna expect. One of the things that's really tricky is like with high winds. And that location, I don't know if you've been to Chicago, but the winds are intense, especially in the area that you want to see, which is in the night or the evening transition, early evening and morning transitions. So that's kind of difficult. But in some other places, the drone is really nice for getting like a if you notice like all of these towers here, like this is getting probably ozone, definitely temperature, humidity, all those kind of things. We have one on top of our trailer. There's one on top of this trailer, on top of here, right? Like that's not really right on the ground. Um, and so you can get more of like a horizontal gradient to things. So whereas the balloon, when you let that go, it's just going by buoyancy and it's going to follow the wind pattern. So it doesn't go up in a straight line like the lidar does, but it does get you a more really high resolution in situ observation for um, being pushed by the wind itself. But you can't really get much on the horizontal gradient or like across the water or something like that. So that's a place that the drones can be an accompaniment. Where if you wanted to see, which is something we would really love to do at some point. But this lidar system here is the Topaz system, which is from Boulder, um, and Noah Boulder. I mean, and so they were stationed across the across the Long Island Sound, and their system has, you can barely see it here, but it has a scanning head on it, which is specifically designed to tilt in elevation. So you can get like a zenith scan, and it also rotates too. But it's more important to get that zenith scan, so you can get sort of like a profile of the ozone. Um, in this case, we're doing it over the water, which is really nice. And that is like that one of the like crown jewels of the network, honestly. But you can get something like that perhaps from a drone system, if you can keep it stable enough and really be strategic on the way that you take the measurement. You could fly it like at a constant altitude over the water and really characterize how your ozone is forming, usually at an increase in production rate over the water. And that's because the actinic flux, the amount of radiation is much higher because water acts kind of like a mirror. So you're getting more reflection than you would like over the grass or something like that. So you get more production. So yeah, there's a place for it in this work. It just wouldn't be replacing anything.
Sure. No, thanks for that explanation. So we have a question here, Elizabeth Uday. What benefits might enhanced air quality monitoring networks provide for public health or environmental management? I can repeat the question.
Yeah, I'm reading. I found it.
Thank you.
Um, what benefits might enhance air quality monitoring networks provide for public and networks to provide for public health, like better provide? Like what could be, if I'm understanding this correctly, is the question that what should we improve to our air quality, our current air quality monitoring networks so that they better serve the public and environmental management? Is that the question?
Elizabeth, you can clarify in the question and answer box. She
Yes,
and
okay. Um, so one thing that I have to say is so Maryland's doing a fantastic job with the density of this network. And I use this one. This is really just the um ozone sites that are in Maryland, but there's also a whole bunch of others. There's a lot more sites that are specifically for meteorology. So weather is much more it's much bigger than air quality is. So that's covered really well in Maryland. There's um, along with just this part of the ozone network, there's also a lot of like um, measurements on all the other molecules, and of course, by all the other, it's really like five. And then there's the particulate matter that's being measured in the network. Maryland also has a it's I believe it's like two auto GC it's gas phase chromatography, so that's able to really get you like a detailed chemical analysis of what's in the air. Then there's also canister samples that are being taken, I think, at one or two sites in the state, and those get sent to a lab and then fully analyzed as well. So, um, and uh, the I don't believe the auto GCs run all the time, but I believe they get switched on um, specifically during the perceived ozone season. Um, so my answer to that would be that uh, to follow in creating dense, high resolution networks. Notice most of what I mentioned was about specifically on the surface, but I think it's really important that you know you can see what's happening before it gets to the surface, or at least at the same time. We kind of only have, or I should say, kind of had ish this site here that gets you sort of like a um, I call it a super site because it's exceeding the expectations of most sites. um, but there's also at 12 here and one there's um, a wind profiler as well. So Maryland's doing like really good in having a network of uh, a network of instruments that lets you understand and tell the story of what's going on with the air. New York has its own version that is, of course, they have more sites. It's a much bigger state, um, and they're also doing really well. California's got its own thing going on, but uh, it's really the answer is to take more measurements, and then the other part with that is to be strategic with where you place the measurements. That's one of the pieces of my work now in a postdoc at NASA is to kind of figure out uh, 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 the optimal placement of these types of sensors, these new perspectives, right? Like if I'm going to be deploying all of these instruments, where should I put them to get the best sort of like, you can think of it from an economics perspective as well. It's like, what's the best bang for your buck in building a network? And then from a science perspective, where is it that we need to understand the most? And kind of like blending those two together. Because one of the things is like, you know, uh, an ozone sonde is going to cost like, it can cost you like $2,000 to launch it. And then sometimes you like don't even get it back. Most of the time, really, especially if you're near the water. Um, and most of this stuff is biodegradable. Um, so that's one perspective, is like, what's the frequency that you want to launch those things? Or can you add in drones to cover some of the other spaces? Or when should you switch on the lidar, and what frequency? What's the resolution that you need in the vertical? How far away do you need to place each of these profiling instruments? Do you need, like, which type of ceilometer do you need to buy to get to the right um, profiles that you're trying to see? What's the frequency that you need to run your passive instruments at? Like, where do you specifically place them in your environment? Do you need to like clear off a patch of land to get it here because this is where the best science is going to happen? Or is it fine to just slap it on the roof in the middle of the city and that kind of thing? So two parts to that. More measurements that are like this, and this is also kind of like a new thing. Most of these networks, I mean, ozone sondes have been around for quite a long time. It's a really simple measurement where you just take like potassium iodine reacts with ozone, and then you get two electrons, and you can just measure that on a circuit. Very simple, really old technique, but things like um, reliable ozone lidar, commercialized ceilometers, which are like aerosol lidars, and then networks like Pandora and Aeronet. Those have only come to be around in the last 20 years and are like kind of finally at a density, at least in this region, where you can really get to um, the level that you need.
All right. Thanks so much for that explanation. So it seems like we are running towards the end of our time. Elizabeth says thanks for the nice talk. So yeah, we definitely enjoyed your talk, Dr. Roots, and please join us again for the next KITP and NSBP Innovate seminar. And with that, we bid you adieu.
Okay, thank you.